from her media extravaganza to defend her PhD thesis. Stacy came to Northwestern via the University of Wisconsin-Madison, where she was a civil engineer. And since her arrival here, she has been nothing short of an exemplary graduate student. I have a long list of things to read that she has done since she's been here. Almost right off the bat, she won the Stephen Rothblatt Scholarship from the Air Waste Management Association. She was selected by the American Geophysical Union to represent Illinois during a congressional visit day. She was selected by AGU to be a fellow on their Voices for Science program. She was selected to be a National Science Foundation Ideas Data Science Fellow. She won the department's Cohen Graduate Service Award and just this past spring won the Horace A. Scott Award for Outstanding Graduate Research, which is our department's highest scholarship honor. He has 3 thesis chapters. The first is published in the journal JGR Atmosphere. And the second is an environmental research letter and just received minor revisions. And the third is in preparation. In addition, and very uncommonly, Stacy has been a co-author on a huge number of studies. She has 5 other co-authored publications in addition to her thesis chapters. And much of her research I am thankful for because it also has informed some of my grant awards, including my most recent grant award. So without Stacy, that would not happen. In addition to all the academic accolades, Stacy is a tremendous science communicator. And in fact, it doesn't always happen that you spend 5 or 6 years of your life doing research, and then your city gets slammed with the worst air quality it has ever seen. And it turns out that puts you in demand. And Stacy is on a first name basis with a number of reporters in the area, and very recently was on our local NPR station, WVUZ, to have a long conversation with Sasha Ann Simon. And it is a masterclass in science communication, and I highly encourage you to listen to it if you haven't. Stacy steals the show. She's there with a number of very prominent people that Stacy blows over the top for. And I encourage her for this thesis defense to actually just play the podcast. But then we decided that we didn't want to face the wrath of our graduate. So we decided against. Instead, you get to listen to her today, present her defense. The way this works is that Stacy talks to us, and then you get to ask questions at the end of her presentation. When she's done answering all of your questions, we have a closed door defense in which her thesis committee, which is comprised of Dr. Jordan Schnell, Dr. Trish Meadows, and Dr. Yara Axford, we get to ask her all the questions that we want to ask her. If she is successful, we get to drink champagne. So wish her luck, and thank you all for coming.
Hello. Maybe too loud. All right. Hopefully that works for everyone. Yeah, thank you, Dan, for all those nice things. I don't know what to say. I think all of that was possible by you, but I guess I'll wait for my thank yous until the end of this presentation. So let's get started, guys. The reason why we're here today, besides me, obviously, is the choice that I decided to study air pollution for the past 5 years of my life. I'm studying air pollution because millions of people are dying every year from pollutants that we're emitting billions of tons of. This number is really insidious. it's not necessarily out in the open like car crashes, AIDS, viruses, but it is causing more deaths than all of those really violent causes. Even at acute levels, we experience air pollution by seeing higher rates of COPD, seeing higher rates of mental illness, wheezing, and asthma. And a lot of these worst health effects are actually concentrated in cities where a high density of emissions and a high density of population interact. Yeah, so humid-made or anthropogenic air pollution has been an urban problem since actually before the Industrial Revolution. In the 1200s, actually, like here I have a picture of the House of Parliament, which is in London. And London is actually one of the first cities that began to regulate air pollution in the 1200s when the king regulated stack heights because of chimney smoke causing health problems in the population. And the cities are the perfect encapsulation of what happens, all the good and the bad of industrialization. We get a lot of economic prosperity in cities, which brings people out of the country into cities. But as a result, we also get this interaction of culture and people. And as an example of this, we've got Monet actually painted the House of Parliament back in the 1850s. And scientists have used these paintings to figure out sulfur concentrations that were happening during Monet's lifetime. And as a result, exactly what caused this city to be so important for Monet is exactly what caused all these health effects. And then fast forward 100 years later, we've got the Great London Smog Event, where over the course of 4 days, London experienced a paradigm shifting air quality event. Thousands of people died over the course of 4 days. And basically this happened because of stagnant weather conditions, as well as the emissions of all these harmful pollutants. This event made international headlines, and this was happening in the 1950s, which was associated with a global understanding between the connection of public health and air pollution. As a result, around the same time, the US was dealing with similar smog events, though with less compelling pictures, really. We see the first real federal legislation into air pollution research called the Air Pollution Control Act in 1955. So yeah, after 150 years after the start of industrial scale emissions, we begin to study these emissions and also control pollutants. And that's because the field of atmospheric chemistry as it relates to air pollution and epidemiology is actually pretty new and really only started in the late 19th century, around the start of industrialization. So yeah, measurements and experiments with ozone, which is an important component of smog, began in the 1900s, where atmospheric chemists like Febvre and Buisson basically hypothesized the importance of ozone in the structure of our atmosphere. What we basically see is this concentration of ozone in the stratosphere, which is the layer above the troposphere, and the kind of interaction of molecular oxygen with UV light basically causes a temperature inversion as it transfers into ozone. And that's really important for this structure that we're seeing in our atmosphere. And also the stratosphere is great. We hear so much about it because this stratospheric ozone is protecting us from a lot of UV light. And then in the 1970s, we actually began to think about how ozone was made in the troposphere. This is the part where we live, and this is when I talk about ozone for the rest of this presentation, I'm going to be talking about tropospheric ozone. And I'm talking about tropospheric ozone because it's detrimental to our health. Dr. Ari Higgins-Smith, he's known as like the father of air pollution control. He came up with the mechanism for, he began to hypothesize basically the emissions from cars, including nitrogen dioxide and volatile organic compounds, VOCs. Those combine together and cause ozone, which was, again, this really important smog-forming chemical. And Dr. Higgins-Smith was the leader of the air pollution control movement through the 1950s and 60s until he actually died of lung cancer shortly afterwards. So that's how we got here. While there were some theories about the importance of air pollutants in the structure of our atmosphere, the funding provided by the Air Pollution Control Act and the passing of the Clean Air Act in 1963, shown here being signed by Johnson, actually kicked off more air quality research and did more, basically establish this network of air quality monitors shown here, where we could actually begin to look at pollution emission sources, control these sources, and also link the impact of ambient air pollution with the health impacts that we already could kind of tell were happening. The legislation that the Clean Air Act provides basically divides different kinds of chemicals in our atmosphere into criteria and hazardous pollutants, but the ones that I will talk to you guys about today are nitrogen dioxide, carbon monoxide, sulfur dioxide, volatile organic compounds. And each of these are kind of made by different kind of emission sectors like cars, power plants, just solvents, paints, deodorants. And then particulates and ozone can be made through secondary processes. So rather than just being emitted by one sector, they're being recombined in our atmosphere to result in this concentration of these pollutants. And then that takes us to the modern age of atmospheric chemistry, which is where my research actually happens. And I think the most important part after the 1960s was the kind of gains in computational efficiency that we got once we could integrate computers into our research. And that really revolutionized atmospheric chemistry. And basically everything that I'll talk to you about today has to do with computers. Specifically, the kind of computational gains that we got from this movement is that we got better, cheaper, faster, more connected, low-cost sensors. We also then were able to look at pollutants from space using spaceborne observations. And then also we began to use these really complex numerical simulations to basically estimate what was happening within our atmosphere. So this comes to what I'm going to talk to you today and how my research moves forward the field that's been happening for, the past 150 years, or maybe even since the 1200s, I guess. My first chapter is going to be about the model that we use, and I'll talk about the model setup for this paper that Dan mentioned that looks at air quality over Chicago and the Southern Lake Michigan region. Next, I'm going to use basically the model, a similar model setup that we had in chapter 1, and then also pull in all these different data sources that were just recently made available, low-cost sensors, simulations, observations, and combine these to look at what is happening with nitrogen dioxide in Chicago. And then for my last chapter, I'll go over the health and social impacts of pollutants, because I spend all this time trying to make sure that the tools that we're using are good, that the model is valid. But again, what we're all here for is the fact that pollution harms people, and this will be just an analysis of how pollution is affecting people over Chicago. So yeah, that brings us to chapter 1, which was published in the Journal of Geophysical Research Atmospheres. And this is about this really cool high resolution air quality simulation that we did with this model called WarpSeek. So you guys are actually familiar with air quality forecasts, whether you like it or not, okay? We just experienced that terrible pollution event that happened last week. And the kind of model that the EPA uses is called like the nowcast forecast. This model kind of looks like this as an output, where the EPA will give these regions as like moderate air quality, unhealthy air quality, so that you can just basically modify your behaviors because of pollution. This simulation is occurring at 12 by 12 kilometers, which basically roughly estimates to 7 miles, 7 by 7 miles. So it's kind of coarse. And if you think about the city of Chicago, that's a couple pixels to describe what's happening within the city. But for things like long-term health impacts, thinking about cancer clusters, it really makes sense for us to get finer scale resolution. Studies have shown that higher resolution simulations allow for us to be able to better capture spatial variation pollution and then the resulting health impacts. If you think about a city, different neighborhoods look so different, but if the pixel is 12 kilometers, it's going to be the same model. So as a result, we get all this additional information when we bring down the model. Here I have our 1.3 kilometer model output. And as you can see, the yellow areas here are a lot different than what the EPA is showing. This isn't really apples to apples comparison, but you're really getting these fine scale features that you weren't seeing before, like the highways and just this like swirling transport that's been made available. So yeah, let's take a step back and quickly, and unfortunately, I do have to explain how chemical transport models work. Okay, it's not that scary yet. Basically, the first models of atmospheric flows actually happened in the 1890s, which is kind of crazy to think about. These equations were called the primitive equations, and basically what you saw with these primitive equations is that it's how do you model air, which is a fluid just like swirling on a globe. Crazy. Okay, people were hand computing that. Now we've got models, but also we've increased the complexity. So you can think about basically the modeling domain looking like this. Okay, we've got a bunch of little boxes, and each of those boxes basically represent one segment of the atmosphere. And within these segments of the atmosphere, what we're doing is simulating energy flow and mass. Okay, how simple, guys. Energy cannot be created or destroyed. That's what we're simulating. And that's what this equation is showing here. Okay, like the number of molecules over time. And that's another component. As time moves forward, we know chemical reactions happen, which is this part of the equation right here. And we're taking these small steps in time and things are moving around, okay? And that's what this box model is really showing. And the kind of simulations that I use are based in first principles, which is a fancy word to say that our simulation is based off of what we know about physics and chemistry of the environment, okay? We're not just guessing. This is we're doing mass balances, we're doing energy balances. We understand what's happening. We're using our observations of the environment to create simulations. And yeah, now the model that I'm specifically using is called WRF-CMAQ, which is the Weather Research Forecast Community Multi-Scale Air Quality Model, which is, yeah, a lot. But WRF-CMAQ, and when I say it's two-way, basically, there's a really cool part of this model that allows for feedback between the chemistry and the weather. And that's important when you think about particles, which can both like absorb and reflect radiation, and as a result, change the weather. So that's a really exciting like addition to this kind of model that we're using. And then this is how the model works. I'm not going to go over this unless someone really wants to. We can circle back. Instead, we're going to talk about this. This is actually how we set up the model. The way that we have to run this model is that first we run the weather model. This is like the advection and transport part of everything. We're getting temperatures, we're getting relative humidities, and all of those things are important because the next step that we do is we run the emissions modeling system, which is called smoke. Smoke has information about area sources, which are the non-point sources, things like buildings, point sources, so energy generating units or power plants, as well as mobile emission sources, which are cars and all different kinds of cars, light duty cars, heavy duty cars. We simulate all of those together. They're getting influenced by the weather. And then finally, we have the inputs that are available for the air pollution model, which is called WRF-CMAQ. And WRF-CMAQ, it's simulating meteorology, it's simulating chemistry. There are hundreds of variables that are basically reflecting, creating best estimates of what's happening in our environment. And for the output, I'm looking at only 4 months of 1 hourly meteorology and chemistry. The resolutions of this model that we're running it at for this output is at 4 kilometers and 1.3 kilometers. So we're getting like under a mile. And then we're also going to focus on criteria pollutants. One kind of like pushback is that very long title of Southern Lake Michigan domain. That's what this area is. And the reason why we actually have to kind of cut down the domain from something like the entire United States to something small like this is because of just like the sheer computational intensity. We're running 4 months of simulation at 1 hour time steps. I did the calculation. It's about 17 real days of computer time consistently running over hundreds of cores in order for us to just get this output. So it's really computationally expensive to run these models. So we try to be smart about it, cut to domains that matter to us, and then also cut to time periods that matter. And as a result, this is what the output looks like. It's this. Here I have the criteria pollutants that really focus on nitrogen dioxide, ozone, and particulate matter. So nitrogen dioxide, like I said in the beginning, it's associated with car pollution, and that's what you really can see is like these veins of car pollution, and really concentrated. That big yellow spot is Chicago. If you look at ozone, it actually has kind of the opposite footprint of what's happening with nitrogen dioxide. Ozone is highest over the lake, and that's actually something that happens. The lake freeze pulls in precursor pollutants from land onto Lake Michigan, and then it kind of bakes up all this ozone, which is important for the Chicago chemistry. And then particulate matter, this is the pollutant that's both made secondarily in the atmosphere, so it's kind of coming from everything. But also it is being directly emitted by cars, by power plants. So that's why it's a lot more similar in spatial footprint to nitrogen dioxide. And the 4 months that we chose are representative of like 1 month in each season, basically. We've got August, October, January, April, and depending on the pollutant is higher or lower. So nitrogen dioxide and particulate matter are higher in the cooler months. Ozone is definitely higher in the warmer months. And for the other chapters, we're looking at a 4-month average, which we call the annualized pollutant, to just basically get like a proxy for long-term exposure over this area. And kind of the purpose of this paper really was to compare this model simulation to EPA observations. Did we run this model adequately? And we did. It meets previous benchmarks. Right here, I have basically the GIF, the kind of like swirling transport that happens. Here's ozone. When it's really dark, it's a lot of ozone. And then around the domain, those circles, those are actually EPA observation stations. So you can see that it's not necessarily all over the place, pretty like located around Lake Michigan. And also one thing that we find with ozone is that ozone is kind of biased high. The model is this blue line here, and you can see it's kind of offset. That's kind of expected from this model. But also another thing is because we had to run the model the way that we did, we could actually compare the 1 kilometer and 4 kilometer simulation. And what we see is the finer scale resolution model looks better compared to the 4 kilometer model, which is really interesting because we didn't really change the emissions. It's just being able to get down these finer scale characterizations are more important to being able to compare to EPA stations. And most importantly, the details that we get are really important if we're looking at high impact areas. So like the city of Chicago, 3 million residents, 3rd largest city in the United States, okay? There's really strong neighborhood characteristics. It's really important that we're getting these details. And here I have the emissions gridded. This is what the grid cells look like over Chicago with the 1.3 nestled in the 4 kilometer. Here's the 4 kilometer NO2 emissions compared to the 1.3 kilometer NO2 emissions. Something that obviously jumps out is like the highways are not being as well reflected in the 4 kilometer output. And that is really because if you're looking, there's like 61 pixels here. There's like 549 pixels here. What we're getting is about less than 1 pixel per neighborhood over Chicago compared to 6 per neighborhood over Chicago. So yeah, I think that is what's really impressive about this model output. And what is most, I think, unique about this is that now we get to look at the city of Chicago, look at actually near highway pollution. It's not being averaged over a neighborhood. We're getting these really fine scale characterizations. And once again, here's nitrogen dioxide, ozone, and particulate matter. Nitrogen dioxide and ozone are opposite of each other, and that's because of the chemical relationship between the two. So we see ozone lowest over highways while NO2 is highest. Particulate matter, it's highest, along roadways, but also in industrial areas and like really heavily populated areas as well. So yeah, from chapter 1, we basically can say that the model meets EPA guidance for model performance. Yay, we can keep using this model. We also find that there's, just holding most things constant, the finer resolution model does better than the coarser resolution model. like marginally, but it's interesting that it does better. And then also that pollution is really heterogeneous over the domain, but also within Chicago, there is neighborhood scale variation in air quality. It's not just a generic blob. It's important that we get that information. But there are several outstanding questions that this first chapter kind of sets up that I'll talk to you guys about for the rest of this presentation. First, how confident can we be in our simulation without the dense observational coverage? I showed you guys that swirling kind of map of ozone in all those stations. There's like 70-ish stations, but then 90,000 grid cells in our model simulation. So we're getting less than 0.1% coverage. So how can we, refine our confidence, particularly in high emission areas when we do suspect that there's high variation in emissions? And then also, of course, who is being affected by pollution and what can we do about it? These maps, they look scary. This is where pollution is highest. Now, who is experiencing that burden? What is that burden? And what can we do about it? Which we'll get into for the next chapter. Yeah, and this brings me to chapter 2. This is a project that I did last summer with Microsoft Research. Microsoft Research put out 115 sensors into the city of Chicago, and this was a really exciting kind of innovation in like urban sensing, because there aren't actually that many high density, low cost sensor networks. This provided us new information that we've never had really access to before in a centralized place. And specifically, we could look at nitrogen dioxide, which is also not typically looked at with low cost sensors. So yeah, given that I have this model simulation, we've got this low cost sensor network, and then there are also spaceborne observations that are constantly taking snapshots of air quality. Basically, what can we do with these with this outcome? And as a result, this study was motivated by how do we handle data set agreement and disagreement? Okay, the gold standard is EPA observations or EPA measurements, but what are we going to do when the data disagrees and there's no EPA station to tell you what? Yeah, and then once again, the low-cost sensor network that I'm using is the Microsoft Eclipse network, 115 low-cost sensors over Chicago, providing kind of full coverage. I'm using TROPOME satellite observations. This is a polar orbiting satellite, so it's taking daily snapshots of air pollution at a 5 by 3.5 kilometer resolution. So we're getting closer to neighborhood scale snapshots. And then I use the two-way warp CMAC. We look at 2 different months. In my first chapter, we're looking at August 2020 or August 2021 and February 2022. When the Eclipse network was put out, and we had good solid data from it. So yeah, this is the output. Oh no, they look different. I was really upset when I got this data back. I was really expecting it to just be like home run. They're all performing similarly against EPA observations. They're all supposed to be capturing the spatial variation of NO2 over Chicago, but they don't. They don't look the same. They kind of look the same, like there are features that are definitely similar across data sets, but it isn't just like the model. It's so obvious. Highways are important. We're kind of seeing like, hotspots in the Eclipse network, and then same with the TROPOME satellite. Like there's definitely something happening on the west side. So beyond just doing a grid cell to grid cell comparison, how do we get more information out of this? And basically to that, I decided to ask, like, what are we interested in for this data? And what I'm interested in is like, we're using these tools to find high impact areas. How about we look at these tools and have them tell us where are the high impact areas? So as a result, I use this clustering algorithm called the GETIS or GI star clustering algorithm. Basically what this algorithm returns is a z-score, which basically tells you the standard of deviation above or below significantly high NO2 areas for each of these products. So I put each of these products onto the 1.3 kilometer warp CMAC grid. Here, all these little dots, those are the Eclipse sensors. and I have to interpolate it to the same grid. Same with the satellite, kind of downscaling the passes. And then as a result, we can compare each of the products. So I run the hotspot clustering algorithm over each of the data sets. So here's the model, here's the satellite, here are the sensor observations. And now we're getting closer to kind of more similar information. The hotspots that are being picked up by each of these data sets are more similar. But then that becomes really interesting because where are the areas that they are actually dissimilar, and what can we do about data set disagreement? Like obviously in the center of each of these tools, so here's the low cost sensor eclipse, Probomi observations, and warp CMAX simulation. All three of these data sets saying it's a hotspot, great, we know that's really bad. There's no EPA observations, but we can say that there seems to be something happening here. But anytime there's disagreement, we can get additional information. So as a result, what I did was I basically separated out these clusters into high agreement hotspots, medium agreement hotspots, and low agreement hotspots. So this is where we've got consensus. 3 out of 3 data sets are saying that this is an important area. And then we've got the medium agreement hotspots where we've got overlap. That's kind of interesting. And then the low agreement hotspots where it's just one tool says that this is a high elevated place. Taking the consensus hotspot, we basically can say with some degree of confidence that this is where nitrogen dioxide pollution is worse. We've got 3 independent tools, totally independent methodology, saying that this is a high pollution area, and it's really clustered on the west side of Chicago. This is an area that we can look at for intervention. We also looked at the land use and social characteristics of this area, and it's an industrial corridor, and also it has a high population of Hispanic and Latino people, which is an environmental justice priority intervention area. And then looking at the low agreement hotspots, we can basically systematically and automatically identify interesting areas of disagreement. So for example, there's this highway feature in August 2021 right here, right? It's on the north side. And then for some reason, it's picked up by the model and sensor in February, but it's not picked up in August, only in the model. So that's kind of interesting because you would expect that areas of overlap to be similar. So what we then discovered basically is that that highway area, we decided to pull all the sensors near highways and basically average what are sensors near highways saying. And we discovered that depending on the highway elevation, these highway sensors are telling us different things. And that's basically what I have here with these blue marks. At the elevated highway, which is shown right here, is this lighter blue, and the recessed highway, aka this open cut under like I guess not really underground, but whatever, below street level highway is here. And we see across both months, with it being less significant in February, both months there's this like jump in between what's happening at sensors near above elevated highways or recessed highways. And that's basically because we hypothesize that like there are just some emissions that are coming off the recessed highways and hitting the sensors, while this like huge amount of nitrogen dioxide on these elevated sensor or elevated highways are not being captured by the sensors, because the sensors are consistently at ground level. They're actually put on bus stations, so they're very consistently not going to be on an elevated highway. So as a result, this is an interface that's not really being explicitly modeled in the model, and as a result, we wouldn't expect that like the model and the sensors to have agreement at this really hyperlocal interface. But it's something that we're capturing and something to think about also, like when you're walking past the recessed highway, now you can think about what you're doing for public health. There are implications for recessed highways versus elevated highways. So yeah, through using this hotspot analysis, we can find areas for monitoring and policy intervention, which is one of the outstanding questions that I had, was how do we handle data set disagreement, or how do we engender confidence in our model simulations? And then also, yeah, just narrow down why is the data disagreeing? Like I was kind of upset when I first got that data back and it all looked different, but then, you know, you're thinking about it and they're actually measuring different things. So it isn't necessarily that the data, any of these data are wrong, but instead like, what can we do about the data as it is? And then that finally takes us to us being exposed to pollution in Chicago. And specifically, I'm interested in looking at the way that exposure and health outcomes are different across the city. And this, I guess, isn't surprising. Air pollution exposure is not equal over the United States. First off, air pollution is higher in cities. We saw from the model simulations, obviously, all the pollution was really, a lot of that nitrogen dioxide and particulate matter pollution was concentrated in Chicago. Like compared to the surrounding areas, Chicago had like 20 to 60% higher NO2 and PM2.5 compared to rural areas. But also the way that cities are set up, cities actually have higher non-white populations. So in this presentation, I'm going to say people of color. By that, I mean non-Hispanic white people, Asian people, Black people, Indigenous, and Asian people. I think I said that. But anyway, when we look at that kind of like racial disparity in pollution exposure, it's in part like the way that cities and rural areas, I guess, are set up, but also like what is happening within cities. So here's the national exposure disparities. Black Americans are experiencing higher particulate matter exposure, same with Hispanic Americans, and then certainly less than the white Americans, and higher than the average exposure overall. And we also have, evidence from previous kind of systemic racist policies, for example, historical redlining, where modern studies on historically redlined areas indicate that those areas have higher pollution, and then they also are still higher, have higher POC concentrations. So as a result, people of color are continuously living closer to pollution sources, and a lot of research has been done that has connected those things together, right? So my question is, well, how inequitable is Chicago's air pollution exposure and health outcomes? Okay, here's like the national disparities. How about we now focus in on Chicago? We have this model simulation that allows for us to actually begin to look at like census block differences in exposure. And then we can also calculate the attributable health outcomes from that pollution. And when I'm talking about inequality, I'm talking about the systematic overexposure to pollution or pollution attributable health outcomes for any demographic group. And over Chicago, I specifically am looking at the white population, the Black population, Hispanic and Latino population. That's because this is about like 30% of the population over Chicago, even though we see this like very disparate spatial patterns in where people are actually living. And we also can connect that to the fact that like these air pollutants, they have distinct spatial patterns. How do we connect these together? And another element that I look at is the way that income influences exposure and health outcomes as well. Just thinking about, there's obviously that is an important dynamic to where you're living, how you're handling the exposure and like the other comorbidities that are associated with those two things. So yeah, and you guys are not wrong. If you try to match up any of these plots compared to each other, it's not perfectly predicted. It's not that where white people are is not where pollution is. There is no strong linear correlation between any of these data sets compared to each other. So we have to be a little bit more thoughtful about our analysis and not just look at just like the linear relationship between pollutants and the people who live there. And also, I calculate the health impacts that are associated in pollution. And these equations are kind of scary, but trust me, they're super easy. We create the attributable fraction, which is associated with the pollution concentrations, and it's dependent on the beta value. And the beta value is basically like the health response to an exposure of pollutants, X. So we get the attributable fraction. And then the rest of the equation, super easy. Multiply, multiply, multiply. This is the population. How many people live here? This is the baseline incident rates of certain kinds of diseases. Specifically, we're looking at all-cause mortality. We're looking at asthma, incidence of adults, and then we're also looking at pediatric asthma hospitalization, so that we can kind of capture like multiple age groups, multiple demographics, and see is there difference across ages, incomes, races, and yeah, look at who's being affected by Chicago pollution holistically. And as a result, this is the kind of output that we see for air pollution maps, for the mortality maps. You can see where there's high and low NO2 attributable mortality. So if we look at just like the basic pollution exposure across groups, specifically, I'm just gonna look at these lower bars, so ignore everything else. The Hispanic population is overexposed to nitrogen dioxide and particulate matter. And then to contrast, the Black population actually experiences the opposite, really low nitrogen dioxide exposure. The white population, this is all compared to the Chicago average, so that's what the 0 is compared to. So yeah, and the actual relative exposure levels are plus or minus 4%. That is different than the national reported kind of averages, which are around like 20%. But that makes sense because we're looking at one single city, and where it's a little bit more localized. Other studies can definitely look at their own cities and see how these things compare. And then we can also look at the pollution attributable health outcomes. So here I've got NO2, particulate matter, and ozone mortality rates, right? And this picture is not as nuanced as this picture, okay? It's consistent that the Black population over Chicago consistently is experiencing higher mortality rates attributable to all pollutants, even though the pollution exposure is not showing that kind of same thing. And it's not actually that. And the reason why we're seeing this kind of difference between exposure and impact is really just because of the underlying health of the population. If we look at compared to the Chicago averages, the Black population experiences higher mortality rates, adult asthma rates, pediatric asthma hospitalization rates. So as a result, they are more susceptible to experiencing negative pollution-related outcomes. So it doesn't really matter what the pollution levels are because the impact is what the impact is. So as a result, we kind of get this dual result where Hispanic and Latino residents are exposed to higher nitrogen dioxide and particulate matter, but Black residents experience higher NO2, PM, and ozone across all the health metrics that we look at. And as I mentioned, we do look at the effect that income has on these outcomes. And specifically here, I want you to just look at this pink dot relates to the Hispanic and Latino population. And you can see that as in household income increases, Hispanic and Latino population consistently experiences higher population weighted concentrations of nitrogen dioxide until we get to about like $150,000 for household incomes. And then this again, across incomes, this purple dot, this relates to the Black population. Across all income levels, the Black population experiences higher population weighted mortality rates. So as a result, household incomes don't really affect the outcomes or the exposure. It's just kind of what is happening across the city. So then that brings up this dichotomy that we have to figure out how to address inequalities in exposure and health impacts. This is kind of complicated map, but I like to think of it as kind of like an X-ray. Here, as you get increasingly pink, that is associated with higher pollution quantiles. So basically, this gray area means like it's got lowest pollution. This pink area means that it has the highest pollution areas. And then this second axis that we're looking at right here, this gray area is lowest baseline mortality rates. This blue area is highest baseline mortality rates. So as a result, like increasing blues means higher baseline mortality. But we can actually mix the data together. And as a result, we're getting these shades of purple. And those are areas of overlap where we're seeing high pollution and high baseline mortality, which actually provides us a kind of, you can look closer into the data and see where is the highest places of impact and also the people who would be impacted by that pollution as well. So yeah, if we're looking at something like NO2, we're seeing like high concentrations on the west side of Chicago and some purple areas here on the south side. Same kind of situation with particulate matter, which we'd expect because they have similar spatial footprints over the city. But then for ozone, it's got this inverse relationship, but we're still seeing areas of purple. And basically in this chapter, I propose how we can use this kind of dual view of air pollution and the underlying health of the population in order to identify areas of impact. And as a result, when you're targeting these purple areas, you can get better equity across the city. Exposure levels go down, health impacts go down, and that's important so that we can start developing smart policy about where can we lower pollution because it's so high, and where can we help people because they are going to experience worse health impacts. So yeah, briefly from this chapter, exposure and impact are not always co-located over Chicago. Also, incomes don't really change the exposure or health inequalities. Hispanic and Latino residents have higher NO2 and PM2.5 exposures, but Black residents experience the worst pollution-related outcomes across all the health metrics. And I think that policies which balance exposure and outcome should really consider both the underlying health and where the pollution is. And that should be just how we create smart policy moving forward. And one example of that is actually some work that our lab has done. I've shown you so many maps. I keep talking about the highways. There's a lot of vehicles causing pollution in Chicago. So what we've done in our lab is began to use this model to ask what if we electrified vehicles? Is that policy good? Is that policy going to help people as in this dichotomy that I just mentioned? And as an example, I'm going to bring up some work that Sarah Camilleri has done about electrifying heavy duty vehicles, because our model can propose a solution, and this is really important for the community of Chicago. They really want better trucking standards. And here, once again, same map, except this time when I'm talking about NO2, as it increases, it's actually blue. And this is also the change in NO2. When we electrify trucks in Chicago, all of Chicago has a reduction in NO2. So increasing blue just means we're actually seeing increasing like benefits of this policy. And then here I have the baseline mortality again. Increasing yellow means like a really high baseline mortality area. And then these green areas are where we're getting a mix of both high impact and high NO2 reduction. And then if you use this dichotomy to think about who is being affected, it's not actually that it's shocking that basically here's the changes in exposure as we're increasing the NO2. This is basically the average makeup of the census tracts being affected by NO2. And while we do see kind of a high Black population in this like low NO2 benefit area, we actually see that this results in actually really high health benefits, particularly for the Black population. The highest health impacts are happening in Black areas. You can see that in this like yellow area here, because even the small change in pollutants is resulting in like really beneficial outcomes for the community. So this is why it's not just about like targeting areas with the highest pollution. It's important that we develop policies that will kind of help everyone across the city. And that's actually what we do. Again, all of Chicago has this reduction in nitrogen dioxide. And yeah, here's me last week talking about trucking pollution, and that, yeah, it's really beneficial that we continue to control these pollutants because it is really unequal what's happening with warehousing and health impacts and everything. So this is definitely work worth pursuing. So yeah, I'm finally wrapping up, guys. Thank you for staying with me for an hour. It makes me so happy to talk about the science that I've done over the past 5 years, because, you know, I may seem silly, but this was cool, actually. Other people think so too, because this is actually pushing forward what we understand about simulations and the application of these simulations. When we're actually using this increased model resolution, we're getting better model output. It's worth, like, basically we're showing, is it worthwhile to spend all these computational resources? And I think so. And also like these maps are really useful for the people who are being affected by the pollution that we're using these maps to simulate. So I think that's what's cool about my work. And moving forward, I think we've got a lot of promise in this field. Specifically, what kind of information does national scale CTM simulations look like? The last slide actually was a GIF of this 4-kilometer simulation that my lab group is working on. And that's like one of the highest resolution CONUS simulations. That's going to be great. And even though, again, like I showed you the 4-kilometer model, we're kind of missing some information about highways. But currently, if the other models are run at 12-kilometer, we're getting even less information. So we're actually getting neighborhood scale characterization over the entire United States. That's going to be really interesting information and really useful for a lot of people. But also, we're going to get these, I'm just going to talk about this one. We're getting geostationary satellites, which means that we're going to get hourly information about air quality. That's going to make us, better at developing models and making these model assessments. It's going to provide us better tools to make rapid response, like maybe these rather than air now, we're using satellites as well to continue to help inform what's happening with air pollution. And these low-cost sensor networks, there's a lot of these really cool developments, and seeing those scales will be really useful. And in terms of like final thoughts of what I want you guys to take away, I want you guys to take away that environmental policy actually works. Here I have the pollutants over time, percent of whatever, pollutants over time, okay, since the 1990 Clean Air Act, which was an important amendment. So over the past 30 or so years, if you average out all the pollutants, we've reduced pollution by half. And we've done that through changing administrations, through several recessions, like through a lot of world changing activities. But because we've continued to pursue the Clean Air Act, continue to make sure that we're following the laws that we set, we've actually seen this reduction in pollutants. And that's really great. And I think that moving forward, we can be even smarter about how we choose to pursue the Clean Air Act and think about how we're setting up our cities. And even on a more global scale, I think that we can use the kind of stuff that we've talked about today. I've been talking about Chicago, but using low-cost sensors, using satellites, using simulation. You don't need the EPA observations and like this really expensive network now to start thinking about what does justice look on a global scale. And that's really important because if we're thinking about things like climate change, these health hazardous pollutants are also emitting carbon. And that's important on the grander scale and the global warming whole thing. So we're getting these climate co-benefits when we're regulating these health hazardous pollutants and allowing countries or other cities that maybe don't have the same kind of like wealth that we do, but we provide this technology. I think that's so important that we continue to do that work. And also I want people to start thinking about people in their science. There's so much that we as scientists can do as long as we check in with like who we're studying with and what we're doing and how are you disseminating that information. Is it getting to the people who actually care about it? Because people in this room, great, but also we need to think about like the community that's being affected. So I hope that you guys can think about how this all connects. We're in a global world. It might be just a car, but we're all in this together. So yeah, these are my final takeaways. You heard it. We can get to my thanks. I'm so thankful and so grateful for everyone in this room, everyone who's helped me on this journey. Dan, oh my God. I'm sorry you've had to handle me, but you're welcome. My committee, like Trish, Yarrow, thank you guys. Like, you guys have provided me so much support and helpful feedback, and I cannot believe it. Jordan, hundreds of hours of training. I can't, again, thank you, and I'm sorry. And of course, my family, my parents, for encouraging me to pursue my dreams, even though they think it's really weird that this was it, you know? Science isn't for everyone, but I guess that's for me. Yeah, my sister always being there, like every phone call, she's there. And of course, my friends, like we have gone through so much life together. There was a pandemic. There was moves, life happening, you know. I'm so grateful and thankful. And without you guys keeping me sane and happy, this wouldn't have been worth it at all. But I'm so happy that we've made it to this point. Yeah, and of course, also thank you to the department. So helpful. Matt isn't here, but Suzanne also being a great DGS. Yeah, and the graduate students, everybody. Oh my God, I'm not good at expressing myself. So read the thank you page, okay? Yeah, and now we can take questions.
Stacy, can you hear me?
Mark. Yeah, of course. So the question was, what is particulate matter? That's a great question. Is particulate matter smoke? Yes. Is the particulate matter pollen? If it's small enough. When I say particulate matter, it actually is kind of a catch-all term for a particle that is less than 2.5 or 10 microns in diameter. And these particles can both be just like elements like black carbon, but they can also be kind of like gas-based sulfur aerosols that recombine and become particles that kind of glom up. So that's why particulate matter can both be formed through these secondary processes, meaning that other gases react and form particles, causing like haze, for example, and smog. But then also it can just be directly emitted. Yeah, like smoke, tiny particles. Okay.
Explain that.
That's a great question, and I'm so sorry, guys, because it's not straightforward. There might have been a reason why it was glossed over. So yeah, nitrogen dioxide is formed through combustion processes. So basically, a huge amount of energy. We've got nitrogen. It's most of our atmosphere. It's 78% of the air that we're breathing. So when combustion happens, these nitrogen atoms basically get blown apart, react with oxygen. We're creating nitrogen monoxide and then nitrogen dioxide quickly after that. So it's pretty direct though. It's combustion, it's creating nitrogen dioxide. Same thing happens like with light or driving our car or running power plants, combustion. Then ozone. Ozone, we can kind of simplify how we think about how ozone is being made by looking at nitrogen dioxide, which is a component in ozone formation, and volatile organic compounds, which again is a component of ozone formation. Depending on the ratio of nitrogen dioxide to volatile organic compounds, you're either going to see like increasing ozone values depending on if you're increasing nitrogen dioxide and volatile organic compounds. There's kind of a balance in the atmosphere. So depending on what kind of chemical balance you're going to create ozone either by increasing nitrogen dioxide or increase ozone by increasing volatile organic compounds. If we look at someplace like a city, we've got a lot of nitrogen dioxide. So actually what we need to form more ozone is increased volatile organic compounds. If we're looking at something like Chicago in certain months when we don't have that. So yeah, ozone is being formed through the emissions of NO2 and volatile organic compounds. And I'll leave it at that. Okay.
With the data aggregation that you use, are you currently or are you in contact with NOAA to essentially use their data platform? You mentioned Microsoft.
Yeah.
Using their data platform or coordinating with their data platform to enhance that inclusion
Yeah.
at a micro level. I mean, when I was a kid, you got the weather forecast, with the
Mhm.
guy that came in front of the, held up an umbrella and said it's for rain. And now we can tell within a few minutes.
Yeah.
If a tornado is gonna come rolling down our,
Yeah.
into our neighborhood. So we assumed,
Yeah.
it seems to me,
Mhm.
that that would be a natural evolution to coordinate that with an existing source of data aggregation.
Definitely, yeah, yeah. So I guess the question is, what kind of data aggregation and what are people doing with this increased model resolution? We've got all this extra data. How are we operationalizing that kind of, right?
My question more is on that data collection.
Mhm.
This seems to me that this is a derivative of that kind of data collection.
Yeah,
Can you coordinate with, because you're talking about cost,
yeah.
can you coordinate that, add your sensors or whatever,
Mhm.
existing structures that are already either going up
Yeah.
or on the ground?
Yeah. In as a short answer, yes, and it is currently happening. Basically, for example, the Microsoft network was kind of one-off. It was more of a pilot research specific thing. In the same way that my model is not actually operational. It's we're using it for research as opposed to trying to spin it up really quickly and provide high resolution forecasts. Like the EPA, NOAA, they all run models so that they can do these like rapid response. But what we do see with these organizations is that they are beginning to use like low cost sensor networks, for example, Purple Air. They're looking at using those sensors in order to like better inform the kind of forecast and everything that's happening. So there is like, there is a lot of conversation between people. If you're looking at like new satellites that are being launched, we've got the European Space Agency and NASA working together to launch satellites. We've got a lot of different coordination across governments. I think the difference between my work and then, for example, like these people who are doing a lot more observational and public facing work is that, we have our data accessible on one website. While, people like the EPA, NASA, would be great if we could go to one website and get all that information. But I think moving forward to the kind of user friendliness of this data is definitely something that's constantly being reevaluated at these organizations and like where you can get it, how you can get it. I think that's why there's a lot of like private weather companies. They're not really, they're using like government data, but then it's easier to use. So maybe the government can continue to make it easier to use. So long answer. But we got no one in the house. Yes, Pat. That's a great question. Did the data show any impact from railroad operations? Short answer, yes. The city of Chicago has 16 intermodal stations, and these are huge hot button topics for particularly community activists. And our model does simulate these intermodal stations where we've got trains and then basically all this cargo being taken off of trains onto trucks, and these trucks being going wherever, the rest of the United States. We do simulate that. However, I think this is an area of active investigation that we're using in order to like better refine these significant point sources. We're not working on that yet, but we're constantly asked to. So I'm imagining we will start working on that. There's questions on chat. Alex, you can get. Yeah, that's a great question. Do I have to worry about population? I think the data that I'm using to do these like health assessments are, I'm using the American Community Survey, which is like a census-ish data set that includes the population over a 5-year average. So the model simulation that I'm using is using data within that time period. So with that being said, it's not like these results are forever. This model would have to be updated. The data for these health impacts have to be updated. Hopefully when we update it, it's because we did some smart policy based off of this, and then we can start testing how good we were at ameliorating pollution and impacts. But So yeah, it matters. Yes. Mm-hmm. Mm-hmm. With height. Yeah. That's a great question. And in part because um I don't have I can't tell you really an informed answer, but I can kind of think it through. Uh, it just depends on the atmospheric conditions, how close you are to an emission source. Like in general, when we're thinking about exposure and health impacts, we're looking at like really long time scales and like broad time scales. So we're also thinking about like you're being consistently exposed to a certain level of pollution. So yeah, like that high impact, I don't really know, but that's a great question. And we have the technology, so we could ask it. Yeah, like plumes matter, but yeah, I couldn't tell you. Yeah. Mhm. Yeah, yeah, that's a great question. Some background, Chicago is in non-attainment for ozone, so that means that we're experiencing basically like illegally high levels of pollution according to the EPA. And one reason that we do experience that, or at least that scientists in the area have been thinking about, is that there's this lake freeze. So lake areas coming off the lake and coming inland. And sometimes what we can see is that some of those lake freeze days, they come inland and then they spike the sensors, the EPA sensors that then basically put us out of attainment again. So that is basically, yeah, like the fact that we have the lake acting as a reservoir for ozone, we do see it associated with like when the lake breeze comes in, we're seeing higher ozone. But also like, does this mean that you are always going to have a bad day by the lakeshore? No, depends on the wind direction, depends on how much ozone is on the lake that day. Like day-to-day variation in pollution is higher than the spatial variation in pollution. So it really depends on the day. And that's why it's still like best standard to look at what the EPA is saying. Is it an air quality action day? Should I stay inside today? Should I make sure to close my windows? Like that is our best data. Yeah. I'm gonna get some online. Yeah. Maybe areas where bottles or there's that's a great question, Lewis. So does my research inform where we should place sensors? I'd say yeah. The red area that I highlighted, there's no sensor there. There's no EPA sensor there. It's the EPA has these like stringent qualifications for where they can put sensors. And they're typically in like fields. They're not directly by pollution sources, but that's because the Clean Air Act is monitoring ambient air quality. So we're thinking about the background. They're not necessarily interested in figuring out how polluting this highway is. They want to know if the city of Chicago in general is okay. But as a result, they also have some like on-road highway sensors that they just don't use for necessarily like enforcement purposes. So this is fine. We know that air pollution is really high. We want to know what's happening in that pollution area. Let's put a sensor there. Yeah. Mhm. Yeah, that's a great question. The question is, are electric vehicles feasible for Chicago? I think the truth is we're going to have to do a lot of infrastructure work over the next coming decades. Certainly. How are we getting pollutants? Pollutants. How are we getting energy? And what's happening with the pollution at those energy sources? Right now in Illinois, we have a lot of coal and natural gas powering our energy grid. It's important that we continue to transition away from that, but also have the capability to scale as we're also transitioning away from gas powered vehicles to, for example, electric vehicles or other kinds of movements. I think it is possible, but it's not possible if we just pretend like we can do nothing about it, you know? We definitely have to be smart and scale up the kind of energy and how we're going to work that. Yeah. For like more equitable, like what would you say for changes for policy for helping out in those for getting affected? Yeah, of course. I think that this is kind of one of the times that I don't think we can talk about like climate justice without talking about like the social infrastructure that we have. So like one of the things is like, is the problem there that we have too high of pollution, or is the problem that we have like terrible healthcare? I think in these areas, it's really important to make these higher incidence rates of health outcomes that can be addressed, as well as the pollution that's available there. So I definitely think making our healthcare system better and more equitable it's also going to result in the same kind of environmental justice outcomes. You know, like I showed you the math, it's pretty simple. So yeah, I think we should definitely first off just make sure that we continue to expand healthcare access, expand reach into those kinds of communities. But then yeah, the Biden like climate justice plans, they come up, they say that they're prioritizing environmental justice areas. And I think that one framework that we should think about is what is the health of the community. Maybe that should be considered when you're also thinking about pollution intervention plans, because those areas are going to experience really great health outcomes because of reductions in pollution. Suzanne? Great. Yes. Mm-hmm. That's a great question. Okay, so how do I handle the data when I upsample across grids? So the only upsampling that I presented today was actually the grids were perfectly aligned. So all I had to do was do an area average of these 1.3 kilometer pixels up to that 4 kilometer grid cell. So I just did basically average, like adding. So that's not too complicated. And then for biasing when I am down sampling, could you repeat that, the biasing when I'm down sampling question? Could you, what is spatial aliasing? Yes, okay. Mhm. Yeah, that's a great question. So what happens to NO2 when it gets whisked away from Chicago? Basically, it reacts in the atmosphere with other pollutants relatively quickly on the matter of several hours. And so it can become, for example, nitric acid, it can be reduced. It can also just be like rained out. It can be absorbed by plants. Yeah, it doesn't stay in the atmosphere for very long. So these are very short-term pollutants that we're talking about. Mm-hmm. I don't know. Not this one. This one? This one. Oh, well, take that up with NASA because I mean, I have had this problem myself, but basically what has happened is they don't have Lake Michigan. So this is the state boundaries, and that's why it looks so weird without Lake Michigan. But this is a GIF I downloaded from NASA, so not my problem. Yeah, I guess one last question. I'll take it online. Is there any last online ones? Yes, sir. Okay. I'm curious how you decide to place and study what That's a great question, Elise. The question being, were the sensors informed by my model? I did not place these sensors, actually. Microsoft had already decided how to place the sensor network, and how they chose those locations was so that they could be an equally spaced mesh grid, so you could interpolate these values and get some kind of representative information. But they also reserved some sensors for community groups so that they could also, go into the community and say, where do you think pollution is bad? So it's got also some like community information as well. So that's how the sensors were placed. All right, I guess I got it.